Okay, so I'd like to begin section 7.2, which is entitled Counting Our Way to Probabilities. What does that mean? Well, classical probability is a fraction, right, built out of number of things, number of ways an event can occur divided by number of items in the sample space, number of total different ways that an experiment can, the total outcomes of an experiment. So we need to be able to know how to count larger sample spaces. For instance, if I said, what should the question be? What should the question be that's going to motivate this counting, these counting techniques? Let's say, what is the probability of unlocking a phone that has a 4-digit lock code if you only have 3 attempts? So intuitively, you might already understand that it should be 3 out of something, right? 3 out of some large number, right? So we already have an idea of the size of the numerator in our classical probability. The number of possible outcomes in the event, right? So let me say a little bit more about that. The event is unlocking the phone, right? That would be like the event succeeding, right? Unlocking the phone is the event. And there are 3 possible ways to make that happen because you have 3 attempts, right? So typically, you know, the numerator, at least in these early problems, the numerator is not going to be the issue. It's going to be the size of that sample space. How many different possibilities are there for a 4-digit lock code? That's really the question. So the real question, the question that So the question that we will learn to answer in this section is, how large is the sample space? And we're going to need to learn some new counting techniques. And also, we are going to apply the counting techniques to the event space as well, like how large the event space is, but at least at first we're really just concerned with finding the size of the sample space. So we need some new counting techniques. Okay, let's think about this one. So what I'd like to do is draw a picture, maybe, or some kind of diagram that will describe how many different possibilities we have for a 4-digit lock code. And based off of this example, we will build a process that will allow us to find the sample space for other problems that might be similar to this. All right, fresh piece of paper here. 4-digit lock code. Okay, let's think about that. Let's think about that 4-digit lock code. How many possibilities are there for the first digit? Well, on a phone, you can have 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. And we have 4 positions, which I'll just draw 4 empty blank spots for my proposed code here, my 4-digit lock, right? How many possibilities are there in the first position, for the first position? Well, could be a 1, could be a 2, could be a 3, could be a 4, could be a 5, could be a 6, 7, 8, 9, or 10. There are 10 possibilities. There are 10 possibilities. For the first digit. Cool. How many possibilities are there for the second digit? Well, it would be 10 again, right? In fact, there are 10 possibilities, whoops, for every digit. I shouldn't say digit, sorry, I meant position. That's meant position. There are 10 possibilities because there are 10 digits, is what I mean to say. There are 10 digits over here, so there are 10 possibilities for each one of these positions, each one of the 4 positions. Now, what if we knew something about the code already? Like, well, this is grandma's phone, so she probably just uses like 1, 2, 3, 4, or like 0, 0, 0, 0. Well, so we're not getting into that, right? This is just a straight up, completely random code. 10 possibilities. All right. Good. So now what? Now what do we do? What do we do with these 10s that we have? There are 10 possibilities for every position. All right. Sorry if my train of thought got broken there. I got a spam call from JSU, they're alumni trying to get money from me. All right. So where are we? Let's make a diagram to represent this situation going on here, and maybe it'll tell us what we should do with these 10s. All right. So, first position, how about I write out all those 10s? I mean, every possibility represented by this 10. So I'll say, first position. I can have a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, or 10. 6, 7, 8, 9, 10. Okay, this is first position. Now, consider this. Off of 0 into second position. Off of 0, pin 0 down as the first digit. How many possibilities from 0 do I have? Probably you're getting it, right? It would be 10 just off of 0. I could have 0, 0, 0, 1, 0, 2, 0, 3, 0, 4. 10 possibilities, right? Let's see how this goes. This is going to be a lot. Let's see, I have 0, 0, 0, 1, 0, 2, 0, 3, 0, 4, 0, 5, 0, 6, and then I'm going to have 0, 7, 0, 8, 0, 9, and 0, 10. So, Now, you can imagine that drawing this out is going to become a nightmare, right? This was just literally first position, right? I need a similar thing off of the 1, off of the 2, off of the 3, off of the 4, etc., etc., etc. Just in the first 2 positions, how many possibilities are there going to be then? Each one of these 10 digits has 10 possibilities, right? So just in the first 2 positions, how many possibilities? Leaving a blank there. Well, if there are 10 possibilities here, and each one of those has 10, so there's 10 off of 0, 10 off of 1, 10 off of 2, how many is that? 10 times 10. That's how many? 100 possibilities. Just in the first 2 positions. Okay, now you may be saying, oh, so what about the 3rd and 4th position? Well, from 2nd to 3rd, each one of the 2nd positions would then have 10 more, right? So this should give us an idea about what we're supposed to be doing to get into the 3rd and 4th position. Each time, we're multiplying by 10. 10 possibilities, 10 more off of each one of those, then 10 more off of each one of those. So the 100 possibilities here, there's 10 more off of each of those, so that's 100 times 10. And then off of the next step, 10 more. So back here, I know that what I should do is take the product of all of these 10s. Need to take the product of all of the number of possibilities from each position. In other words, 10 times 10 times 10 times 10, which is 10,000. That's it. That's the size of my sample space. That's how many possibilities there are for a 4-digit lock code, 10,000. Now, back here, that means my probability, the probability of unlocking a phone, I already said that the 3 should be the numerator, right? For my probability, the probability of unlocking a phone with a 4-digit lock code would be 3. If you have 3 attempts, 3 out of 10,000. 3 of those attempts out of 10,000. And just for fun, what is that as a percentage? 3 out of 10,000 and then times 100, right, would be 0.03%. So if the code is completely random and you have no idea what it might be and you just guess 3 random numbers, that is the chance that you will actually unlock the phone. Less than 1%. Less than 0.1%. 0.03%. Cool. Now, this picture was not very great because, I mean, it's just too much, right? I can't even list all of them in the 2nd position on one page because there's 100 possibilities just in the first 2 positions. Let alone all of them, right? I mean, there's 10,000, right? Once you get to the 4th position, there's 10,000. So, let's look at a smaller example that I will be able to draw a full tree diagram for. Okay, here's a new question. Let's abandon the probability for a second. Let's just talk about the number of ways to get something, or the number of ways to do something. How many how many choices are there for a pizza at a restaurant? How do you spell restaurant? Such a hard word to spell. Is it, that's what I'm going to say. At a restaurant that has 2 choices for crust, so like thin or regular, 3. Actually, I am gonna write what they are. 2 choices for crust, and I'll say thin or regular. 3 choices for sauce. Say we'll just say like the red sauce. We'll just call it marinara, Alfredo, or pesto. And let's keep it simple. Let's say I don't want to make it too much. Let's just say 3 choices for toppings. And let's make it pepperoni. Oops, pepperoni. Sausage and beef. This place is not vegetarian friendly. Okay, so how many choices are there for a pizza at a restaurant that has 2 choices for crust, either thin or regular, 3 choices for sauce, marinara, Alfredo, or pesto, and 3 choices for toppings, pepperoni, sausage, or beef? Okay, so this is how you do this. You say, well, actually, first I'm going to do a tree diagram, right? That's what I said I was going to do here before we get into writing down the number of options for each and all that. Okay, so first you have choice of crust. So we have, let's see. I'm thinking about how much space this is going to take up. I think I can do it on this page. So first we have choice of crust. And that's going to be either, where is it, thin or regular? Yeah, decided I needed more space. Okay, then off of thin or regular, so this is crust choices, off of thin or regular, we have 3 choices for sauce. So let's do it like this. 3 choices for sauce. That's marinara, Alfredo, and pesto. And the same 3 down here off of the regular crust. Now, off of each of these, we have 3 choices for topping. The 3 choices for toppings are pepperoni, sausage, or beef. There they are. All right. How do I count how many total possibilities there are? How do I count that? Well, what I do is I count up all of the ends of the tree diagram. So this is a so-called tree diagram. It's nice, I guess, to when the numbers are fairly small, but you can already see, even with just 2 and 3 and then 3 more choices, it's starting to get rather, a little bit hard to put on paper, right? So, but let's talk about, if you can get it down on paper, how do you actually use it to count the number of possibilities? Well, the ends of each one of these is representing a full triple, a unique triple of crust, sauce, and topping. Like for instance, if I know all these repeat at the end, right? But if I look at this one, right, let me get something sharper to point with. This one, right here, this, you won't be able to see that. This represents the triple of thin pesto sausage, right? Whereas if I go look down here at this one, which looks like it might be similar because it's pesto sausage, but it's unique because this is regular crust pesto sausage, right? So the ends of each one of these little tree branches represents a unique combination. So if I want to know all the unique combinations, I'm going to count them all up. So I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 total possibilities. Now, remember the last time with that example with the 4-digit lock code, I drew 4 different positions and I wrote the number of possibility in each position, and then I just took the product, right? Let's try that here. How many choices are available in the first position? 2, right? This is representing 2 choices for crust. How many positions? No. How many choices are available in the second position? That like second branch of my tree diagram. 3, right? There are 3 because there are 3 choices for sauce. And then in the last position, choices for toppings, there are 3 choices for toppings. And all I have to do is take the product of these things. If there are 2 choices here, 3 choices here, 3 choices here, I just take the product of them. 2 times 3 is 6, times 3, 18 total. Much faster than making a tree diagram. This is the so-called fundamental counting principle. Now, if you look at the definition for this in the text, it's a little confusing. I mean, it is, I guess, kind of hard to write down what it is. It's easy to show you, but when I write it down, it may get kind of hard to understand when it's written down in its technical, with the technical wording. You can read it, it's on page 315 if you'd like to see the technical wording of the fundamental counting principle. But essentially it just says that if you list out some number of positions or possibilities for something that you're counting, and each one has some number of different possibilities, right? They could all be the same, as in the lock code problem where they were all 10s, or it could be different, as in the pizza one where there was, there was 2, 3, and 3, so the numbers aren't necessarily the same. You just take the product of all of them to get the total number of possibilities. So I'll say, think of these as different groups of choices or possibilities. Right? So like in the case of the pizza, each little line represented like a group, like crust, sauce, toppings. In the code one, each group represented a position in the password. position 1, position 2, position 3, position 4. So how do I say what those are? I just say groups, right? They're just like groups. It depends on the problem, what they're going to be. But you can think of them as different groups of choices or possibilities. Each group has its own number of possibilities within the group. Right? Like crust is its own group, and inside that group there was 2 choices. Has its own number of choices or possibilities. We take the product. Product means multiply, right? So we take the product of all of the number of possibilities. The number of possibilities. To get the total number of combinations. I'll say it like that. Okay, I'd like to run example 1 and example 2 from the text. So instead of me having to write down this entire problem, you can just pause the video, go pull up your ebook in Hawks, go to example 1 in section 7.2, and you can read it along with me. Okay, so it says, in order to log into your new email account, you must create a password. The requirements are that the password needs to be 8 characters long and consisting of 5 lowercase letters followed by 3 numbers. So this password is very specific, and it tells us that we must have 5 letters, lowercase, and then 3 numbers. All right. If you are allowed to use a character more than once, that is with replacement, which they've written in bold there, so we will address that issue. How many different possibilities are there for passwords? All right. So it tells us the password is 8 characters long. Character being, they say character because they don't want to say letter or digit, trying to be more inclusive to one or the other, right? So 8 characters altogether, with the first 5 being letters. So letters in the English alphabet, by the way. And then the last 3 being numbers. And they went ahead and told us that all the letters should be lowercase just to avoid any complications with uppercase or whatever. So there we go. How many choices are there for the first position then? That's what you have to start asking. You have to figure out how many choices there are in each position. Start with position 1. How many letters are there in the English alphabet? That's the question. Well, there are 26. Now, the second position, will it be 26 again? Yes. Why is it 26 again? Well, because they told us that you can use the same letter if you want to. Like if you pick a C in the first position, you can still pick a C again. So there's still 26 letters available to you. 26 letters available to you. So with that logic, then there should be 26 in every single position. Cool. Well, at least for the letters, right? See, I stopped here at the letters. How many numbers are there? There are 10, right? There are 10 digits, 0 through 9. So these last 3 should be 10. What do I do with this? What do I do with these numbers? I take the product. So this is going to be a massive number. A clean way to write this, answer, because I'm basically done at this point, right? With exponent notation, that's a nice way to write this. So 26 to the 5th power, because there are 5 of them, right? 26 times 26 times 26 times 26, etc. 5 times. And then times 10 to the 3rd power, because there are 3 tens. So using exponent notation. But also we can say if we just wanted to write out like actually what this product is, it is 11,881,376,000. So this is a nice, clean, compact way of writing the answer. This is if you actually computed it. This is also a legitimate way to write the answer, just 26 times 26 times 26 times 26 times 26 times 10 times 10 times 10. That's fine. I mean, all of these are the same number, right? It's just different ways to write it. Now, example 2. So following along in the text, example 2 now says that let's change the previous example slightly. The password still needs to be 8 characters long, consisting of 5 lowercase letters followed by 3 numbers. Okay, so I know it's going to be 4, 5, 6, 7, 8. These are going to be my letters. I haven't even finished reading the example, but they told me it's the same setup, so I'll go ahead and set this part up. Okay, and they say, however, now the characters may not be duplicated. So for instance, you can't have like AA or, you know, CC or 00 or 99, okay? That is, we say we're counting without replacement or without repetition. So you cannot repeat letters and you cannot repeat numbers. All right, good. How many choices are there in the first position? Well, A through Z, 26. Now, you've picked a letter now, right? Doesn't matter what it is, but you've picked one. You cannot repeat it. Let's just say it's a D, right? So how many choices do you have here if you can't pick D again? Well, now you have 25, right? Because you used up one of your choices, right? Now, you've used another choice here. Maybe you picked the letter Z here. Well, then how many choices do you have here? You can't use D and you can't use Z. Now you have 24 choices. You see where this is going. Now, next position. You've used 3 letters now. Maybe you use D, Z, and L. How many choices do you have here now? Well, you can pick any letter except for those 3, so you have 23 choices. Okay. And now let's say you've used D, Z, L, and F. So now you have all the letter choices, except you cannot use D, Z, L, or F. So now you only have 22 choices. Good. Now we're done with letters. Done with letters. How many numbers do you have? First choice, you have all 10. But then you've used one. So you see a similar thing's going to happen here. You've used one. Now you have 9 choices. Next position, you've used 2 now, so now you only have 8 choices. There it is. You take the product of all of these. That's going to be your answer. Not really a nice clean way to write this, like no exponent form or anything like that. So we'll just go ahead and calculate it out, and we're getting 5,683,392,000. Good. Right. So example 1 is a good example of the fundamental counting principle at work, where you can have replacement. So this example is so-called with replacement, meaning you can repeat. Let me say it that way, with replacement or with repetition. I like to think about it as with repetition. Repetition. So you can repeat letters and you can repeat numbers. Now example 2 is a good example of something without repetition. I'll say without without replacement or without repetition. Things like that should be stated in whatever problem you're doing, whether or not repetition is appropriate or not. Okay, now since we are talking about products of descending numbers, we're going to go ahead and define something called a factorial. We'll also be using factorials in the rest of this section when we talk about combinations and permutations. So let's go ahead and get this out of the way. So now we're doing like just some math real quick. N factorial, so this is, as the book said, read as n factorial. N factorial is the product of all positive integers less than or equal to n, where n is understood, the given thing is a positive integer. And as a technicality, we define 0 factorial to be 1, which is very weird, but that's just like what we have to define 0 factorial as in order to make all the math with factorials work. So, for instance, we've already kind of started doing, well, at least partial factorials. So for instance, like 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. That's what a factorial is. The product of all positive integers less than or equal to 6. In this case, what are the integers? Positive integers, so not 0. The positive ones less than or equal to 6. Well, you have 6, 5, 4, 3, 2, 1. Take all their products. Is that right? 6 times 24, 120, yeah. Okay. So let's run example 3 now, which is just straight up practicing these factorials. So again, we're looking at these because, well, you see, I mean, we're dealing with products of like strings of numbers like this in the previous examples, so you probably are guessing that these things are going to keep coming up. And in particular, they are part of these things called permutations and combinations, which are 2 new formulas that we'll learn that involve factorials that we will use to count weird things, like, well, not weird, but just new things. So we need to understand how these factorials work. Okay, we got 5 problems here. First one, pretty straightforward. 8 factorial. 8 factorial is the same as 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. If you've got a good calculator, it has a factorial button on it, and you can just click 8 factorial and it'll do it for you. Mine, let's see, looking at the I'm looking at the scientific calculator on, oh, it does. So I can just hit 8, hit the factorial button, and I'm getting 40,320. You could easily calculate this with a calculator, though. Just plug all these in. Okay. Good. Let's do part B. B asks us to calculate 3 factorial over 0 factorial. 3 factorial is 3 times 2 times 1 over 0 factorial is defined as just 1. We just have to take that as the definition, which is weird, I know, but that's what we're taking it. And I don't want to get into like details there or whatever, so let's just take that. 0 factorial is defined as 1. Then that means I have 6 over 1, which is 6. Cool. C is 89 factorial. Oof, that looks rough. Over 87 factorial. But think about this. What's going to happen here? Let me scoot this up a bit. I'm going to have 89 times 88 times 87 times 86 times, and can I just say dot dot dot, and then like at the end I'll have times 2 times 1, right? So I'm kind of being lazy and not writing, well really, I mean, I can't write all those on one piece of paper, right? There's too many. So I'm using dot 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 there to say, you know, to brush the rest of those under the table. Now in the bottom, I'm going to have 87 times 86 times dot 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 times 2 times 1, right? Ending at 1 there. But do you see what's going to happen? 87 cancels. Right, these are all attached by multiplication, so I can do fraction simplification all over the place, right? Because they're all attached by multiplication. The 86 they cancel. In fact, everything in between is going to cancel, right? 85 over 85, 84 over 84, you know, all the way down to 2 over 2 and 1 over 1. Even though 1 over 1 doesn't hurt anybody, but whatever, it can still cancel it out, right? Everything in between. All that's going to be left is the things up top that were bigger than that 87, in particular the 89, 89 and the 88. So that's all I need to calculate here. And I'm getting 7,832. That is going to be a recurring theme in these factorial problems, that you'll have crazy numbers you don't want to calculate, but you realize like most of them cancel out and all you have to calculate is that remaining bit up in the numerator. Part D. D says 7 factorial over 5 minus 1 in parentheses and then factorial. So I know that up top I'm going to have 7 times 6 times 5 times 4 times 3 times 2 times 1. No problem writing all that out. 7's not too big. In the bottom I have 4 factorial, right? Because 5 minus 1 is 4 factorial, right? I do my difference inside, and then I take the factorial. So 5 minus 1 is 4, and then factorial, so 4 times 3 times 2 times 1. And you see again these terms at the back are all canceling, and I'm just left with 7 times 6 times 5, which is going to be 42 times 5, which is 210. So yes, 210. So there it is. Okay, next one was 5 factorial over 3 factorial times 4 minus 2 factorial. So before I write this out, let me go ahead and just emphasize that I'm subtracting inside first. So I'm going to have 5 factorial, 3 factorial, and then 2 factorial. 4 minus 2 giving me the 2 there. So that's going to be 5 times 4 times 3 times 2 times 1 over 3 factorial is 3 times 2 times 1. That's a 3. And then times, so these are attached here by multiplication. So the next one is a 2 factorial, so that's a 2 times a 1. Alright, so I see a bunch of canceling. Let's see, I have this happening. So I'm left with 5 times 4 over 2, right? Because this times 1 is not hurting anybody, it's fine there, so I don't need it. And that's going to be 20 over 2, which of course is 10. Cool. Lots of nice fraction simplification happening with factorials. Okay. Alright, I've decided that I will save permutations and combinations because they deserve their own video. So I'm going to save them for the next video. Alright.